So on stage, I would like to ask to come Markus Spanring, a senior researcher at the Natrans. And topic is from data to precision, fine-tuning large language models for proprietary query languages. This talk will explore the critical necessity of fine-tuning, pre-train large language models to effectively translate natural language into accurate and executive queries for proprietary systems, and the pivotal role of high-quality domain-specific data in this fine-tuning process. Markus, please come on stage.
Yeah, thank you. Very happy to open the last session of today. Hope you're all still full of energy, and yeah, let's get started. So we heard today already a lot about the importance of data and evaluations. So the first part of my presentation will feel like a déjà vu for you, because I will be touching a lot of the concepts, ideas, and problems that were discussed in the previous talks already. In the second part of my talk, I will then go into more technical details, how we fine-tune the large language model for query generation. So to start, let me explain what problem we are actually trying to solve. So our company is in the monitoring and observability field, and we are ingesting a massive amount of data, so petabytes of data daily, in our in-house data lakehouse. And after it's ingested, this data is available for users to do their analytics and get insights into their businesses. And the way to communicate with this data is via our in-house query language called DQL. Now, what is the problem here? Since it's in-house, DQL is not that well known, and it's mainly power users that can use it efficiently. And the next thing is, the data, as I already said, we ingest is massive, and on top of that, it's schemaless. So there is a lot of domain knowledge needed to utilize it to the fullest. So what would we like to have? So it's basically, we would like to translate a user request via some black box into our query language. And you probably already have guessed, we will be using a large language model for that. So what is the initial problem with that? So your off-the-shelf LLM usually also doesn't know DQL very well. So if you would ask it to generate a DQL query for you that shows you the logs from the last 24 hours, it will very likely generate SQL for you. And this is not surprising. It's just LLMs have seen a lot more SQL queries during training compared to DQL. So how can we make the model to generate actual DQL for us? There are two options. Option one is via prompting-based approach. So in addition to our initial request, we also add DQL documentation, so basically how the grammar and syntax looks like, and few short examples. And with this, we can show the LLM what we actually want, and it is able to generate an actual DQL query for us. The second option is via fine-tuning. So instead of adding the documentation or this additional information during inference, we fine-tune it beforehand, and then during deployment, we only need to ask the question again. It already knows what DQL is, and then it can generate a valid query for us. So now the question, what approach to choose? A priori, both approaches are suitable for this task, and I will just outline here the pros and cons that we took into consideration. So the first one, assuming that there is basically no groundwork done, so there is no labeled data available, no eval strategy whatsoever. Usually prompting-based approaches lead to a faster time to first result, while fine-tuning, since there is no data, since you first need to take care of data and the rest, it's a bit more complex to do. The pro of the fine-tuning, however, is that you can use smaller models due to the fine-tuning, also smaller contexts, and this leads to better response times and since it's a smaller context, it's also cheaper. Then additional benefit of the prompting-based approach, you can have adaptive knowledge. So if the knowledge changes or is updated, you can immediately provide it to the model. For fine-tuning, you would need to retrain, because here the knowledge is static and baked in the model. However, this baking in of the knowledge also has its benefits. Usually fine-tuning leads to a higher task-specific accuracy and better generalization. And for prompting-based approaches, they have a bit of a hard time to get this nuanced domain logic, and there is a limited depth of specialization. Then, however, deployment of fine-tuning can be challenging if you don't have something along the lines already set up. Usually prompting-based is pretty resource light and flexible because it's just an API call most of the times. And then a last pro for the fine-tuning, it is more robust, even without large context, since it's really it's trained to output what we want it to output. Prompting-based approaches can be a bit inconsistent across prompts, so they can be a bit sensitive there. So usually, if there is no groundwork done and you go into the prototyping phase, the first point is why most of the people decide for the prompting-based approach, since it has the fast time to first result and you can show off something. However, if you decide like that, there are some pitfalls ahead. The first one is what I call vibe evaluation. So you set some prototype up, and then you test it on familiar examples where you already know what the answer should look like. Then this looks pretty good, and with this you tend to overestimate the robustness of your prototype. Then, since your first results look surprisingly good, you show this off. Your boss basically says, well, that's great, let's ship this into production, because all these edge cases that we can see, we can fix later via prompting, but this is a very dangerous thing to do if you don't understand how the model actually behaves. And the last thing is if you underestimate the importance of data. So if you try to compensate for weak data with longer prompts or longer contexts, this also can lead to pretty bad problems. And all of these pitfalls, if you then go with a prompting-based approach and you have not addressed that before, you can buy a lot of technical depth in the long run when you scale it up, which you then need to tend to. So what approach should we choose? Actually, the question is not what approach should you choose. First, you always should look at the data and your evaluation strategy. The approach itself then comes naturally after. And in the following, I will focus on how we get the data for the fine-tuning, how our evaluation strategy looks like, and as I already said, the fine-tuning step is then last. So let's get to the evaluation metrics that we use. The first metric is the so-called executability, which is simply measuring if the generated query is actually executable. This gives us a single number, and that's it. So we would measure the whole performance with that number. The problem with that is the model could be completely overfit and always generate something very simple, but executable, and then this number would be high, but it's actually a bad performance. So what you would need is multiple metrics. And in our case, the second metric that we have is the so-called retrieval score. So here we don't look at the generated query. We look at the records these queries retrieve, and then we compare the actual records. And this is actually a quite powerful metric because it doesn't punish the model for being creative. So you can solve certain user requests in different ways. As long as they give you the same records, that's totally fine. And this metric will show us that. The fourth metric is the Rouge score, which basically compares the semantics between the queries, so the generated and the target query. Also, this is an example. If you would just use this alone, it's not a very good metric, because if you look closely, I assume you don't know DQL, but I can tell you these two queries basically do the same thing. So this alone would tell us, okay, this is wrong, or not fully correct, but only in combination with the retrieval score, we can see that the model is actually performing well, and we have this cross-check. And the fourth metric we have is the so-called tree edit distance, and here we compare the abstract syntax tree of the target query and the generated query, and this is a measure of the complexity of the query. Okay, now we have our metrics. Where do we get the data from? As I said at the beginning, DQL is not very well known, so there is no large, high-quality labeled DQL data available. However, what we do is we log all executed queries in our internal self-monitoring. So obviously, let's build a synthetic data pipeline out of that. How does this look like? So we have our user who is executing some queries. The problem is what we do is we redact every string in a query because of security reasons. We don't want to log sensitive data like credit card numbers, usernames, whatsoever, before we store them in the self-monitoring. As I said, this is very secure, but it's also rendering the logged queries completely useless for our use case. So what we need to do first is actually re-impute plausible values again. So we get these redacted queries, and then we find plausible values. So for instance, here we have this username John Doe, and then we get a plausible query that has the same structure as the original one. But as I said, it's not the original one, it's just a query that has the same structure, but is plausible. Great. So now we have our re-imputed queries. The problem is, currently we are not able to log the user's thoughts in addition to the executed queries. So we don't actually know what his intentions were when he executed it. So we need to annotate our re-imputed queries so that we get the question and answer pairs. And here we have two options. The first one is using human annotators. Positive side, usually you get high quality annotations, and they should resemble the real world pretty well, but this is pretty expensive and time consuming. Second option is, again, just using an LLM, as we heard in the previous talk. This is rather cheap and scalable. However, these annotations may not reflect the real world, since LLMs tend to generate grammatically correct sentences and are also a bit more verbose, while humans usually are a bit lazy and use shorter sentences. But obviously, we are going for the LLM since we need something scalable. And in fact, this is actually the inverse task to what we are trying to solve. But the inverse task, so going from query to explanation, is much simpler than the other way, because even though the LLM doesn't know the query language, the syntax is very descriptive. It looks a lot like other coding languages, so it just needs to see what the intent is, and then it can give an explanation. So we can get rather high-quality annotations here. So with all this, so as I said, we scrape from our self-monitoring, then we re-impute plausible values, then we add the annotations via an LLM, and this leads to our data set. Now we have the data set, but now we need to derive a good test set from that, on which we then can do our evaluations. A simple approach would be just to randomly sample examples from the data set, but this has several downsides, so we decided for a bit more involved approach. What we do is basically we cluster the data in 3 dimensions. So the first grouping we do is by query complexity, which is more or less the length of the query. The second is grouping by the data source, so for instance, if it's logs or if it's time series data, so on and so forth. And the third grouping is grouping by semantic similarity. So why do we do that? Let's give an example here, again with the executability as a metric. If we would do just random sampling, we can calculate just a single number, since we don't have any structure in that. In this case, we have 90%, so the whole performance would be measured with this 90%, but doesn't tell us more. With our grouping approach, we have now a much richer information here. So on the y-axis, you can see, for instance, the query complexity. So from top to bottom, queries get more complex. So we would spot if the model has troubles with more complex queries or requests. On the x-axis is the data source. So here we can spot if there are certain data sources the model has problems with, and maybe this means that the data is underrepresented, and we can adjust it there. And then each of these tiles contains semantically diverse examples, so that we are not measuring on the same example over and over again. And if you look at the left column, you can see, for instance, for BIS events, that for more complex queries, the performance is degrading a little bit. So this hints at a problem with BIS events. And in addition to that, we now have our 4 metrics, all these groupings, so we have a pretty holistic view of how our models or system is actually performing. So with this, our homework is done, and we can now go to the fun part, which is fine-tuning. But since the heavy lifting is already completed, so we have our high-quality data, we have our evaluation strategy, fine-tuning is actually pretty boring, since you have everything in place, you just need to train your model. For fine-tuning, we resort to the Hugging Face ecosystem, since there we have millions of open source models. So for us, relevant, or what we are exploring, are models in the range of 500 million to 8 billion parameters, so more in the small language model range. Then we look for models that are already instruction fine-tuned, and preferably on code, since this we don't want to do on our own. And then we are obviously looking for permissive licenses, since we don't want to run in any legal problems. Then to the fine-tuning. One way could be to use full fine-tuning, so basically taking these huge models and doing the fine-tuning ourselves. But this usually involves multi-node training pipelines. It's very time-consuming. You need a lot of data, and it's pretty expensive. So I would not recommend going that path if you have not set up such a pipeline already. So what we do is going the parameter-efficient way. So instead of tuning the whole model, we just tune a small set of parameters via low-rank adaptation. So this is very memory efficient. It's actually less prone to overfitting compared to the full fine-tuning. You don't need that much data, and it's also rather cheap. So one training costs us $30, and this takes about 24 hours on a single GPU. So it's pretty efficient. OK, so all the technical details are set up. Now let's get to some results. So on the left side, you can see the results from the prompting-based approach. And yes, we started with a prompting-based approach. In the center is the results for the fine-tuning. And on the right side, you can just see the difference in performance of the 2 models. Again, this is the executability, since this, I think, is the most accessible metric for everyone. Now, I know I said don't use a single number to compare, but I still do it. Already here, you can see that the prompting-based approach, we reach about 70% executability, with the fine-tuning 90%. So this is an increase of 20% overall. But as I said, just a single number. And with our grouping, we can get much more information out of it. So if you look at the rightmost column, which is basically, again, showing the query complexity, you can see that the prompting-based approach gets worse the more complex the query gets, and the fine-tuning is more stable. And actually, yeah, you can see this gradient here. So, but in total, when you look at the right plot, almost everything is green, which is a nice color if you want to measure performance. So we have substantial improvements in all areas. And one thing I didn't mention is this is also while being 2 times faster, using less tokens, so being much cheaper. OK, this already brings me to my summary and the main takeaways. So I've shown that in our case, fine-tuning led to a substantial improvement over the prompting-based approach. And we are faster and cheaper at the same time. Then I can highly recommend to always use multiple metrics to quantify the performance of your model, to always get a holistic view of your system. And as my closing statement, I would have the third part, which is the first step in any AI project should always be data and evaluation. So with this, I conclude my talk, and I'm open for questions.
Thank you so much. Great information that you shared with us. Is there any questions that you would like to ask?
I can't hear it acoustically, sorry. So I'm not sure if I got the question correct. So for the fine-tuning, we use these 8 billion parameter models. For the prompting-based approach, we use an API call, which is basically a call to GPT-4o.
Oh, okay.
So this is prompting-based is based on GPT-4o. Yeah.
So actually, the microphone wasn't needed. Is there any more questions? Okay, I think that we are fine. Once again, applause for Markus. Thank you so much, Markus, for your powerful talk.